Hello, everyone, and thank you, Mike, for hosting this event. I'm excited to talk a little bit about Xcimer and our position on the fusion industry in general. My name is Connor Galloway, and I was roommates at MIT with my co-founder, Alex Valise. My background is physics and nuclear engineering, and I've been working in the field ever since 2009 as a graduate student at the Plasma Science and Fusion Center and Los Alamos. So at Xcimer, we do believe there is a path to electrons on the grid by the mid-2030s, both for the industry as a whole, as well as for our specific path forward at Xcimer. But of course, there are challenges ahead. So I'm going to tell you a little bit about our path at Xcimer, our next steps to get there, our progress to date, and then conclude with a few thoughts on fusion industry challenges. So we have raised at Xcimer over $100 million in Series A capital, and we also won the second largest award in the Milestone Fusion program, next to Commonwealth Fusion Systems. We have 75,000 square feet of laboratory space in Denver, Colorado, over 90 employees, and we've founded the company in 2022. And that's our current facility there you see in the picture with the Front Range in the background. That is where we're building our prototype laser system, Phoenix, which I'll talk about a little bit later, as well as all of our office space for the company. So we are building a commercial pathway for the most proven fusion approach, namely hotspot ignited laser inertial fusion. This is what worked on the NIF, was demonstrated recently, but solid state laser technologies such as those used on the NIF are too costly to scale for commercialization. So at Xcimer, we are using a lesser known alternative to solid state architectures, gas Xcimer lasers, hence the name of the company, just without the E, which are much more affordable in scaling to the energy levels needed for achieving robust commercial gain for inertial fusion. And the low cost can enable great economics to where we have a path to producing electricity with a COE of $50 per megawatt hour. So as I mentioned, laser inertial fusion is the only technology to date to surpass scientific break-even and produce a fully self-sustained burning plasma. Where here is the performance of some fusion machines with tokamaks there, and then NIF laser inertial. And the record gain so far in NIF is a gain of 4.6. So just past April, the NIF achieved 8.6 megajoules of fusion energy out of a fuel capsule with 2 megajoules of energy that were utilized to drive the system. So amazing achievement. What motivated myself and Alex to get started in inertial fusion was actually we learned about what was called the Halite Centurion test program in the 1980s. And this is not often discussed and not well known, but high gain inertial fusion was demonstrated during this program. The key difference here compared to NIF was that in these experiments, X-rays generated from nuclear detonations underground at the Nevada test site were used to drive and implode laboratory scale fuel capsules. These experiments were successful, and the official statement from DOE is there saying experiments conducted at the Nevada test site have demonstrated excellent performance, putting to rest fundamental questions about the basic feasibility of achieving high gain. And the details are classified, but Los Alamos National Lab, Lawrence Livermore, and the National Academy of Sciences all recommended the development of a laser architecture that could scale to 10 megajoule illumination, and that would be sufficient to replicate the conditions in these successful shots. So we're fortunate, based on these experiments, that we know a 10 megajoule laser is sufficient enough energy to enable commercial gain. And importantly, the NIF, National Ignition Facility, is only 2 megajoules because of the very high cost of the solid state laser architectures that impede them from ever scaling up to 10 megajoules. So back to the National Ignition Facility. So here there's 192 beam lines that you see here in the picture, and all of these beam lines are directed to a target chamber and ultimately a whole Raman fusion fuel capsule, and you see the picture here in the bottom right. The way NIF works is the laser energy is used to illuminate the inside of a heavy metal can, and the laser energy is converted into X-rays inside this can. And it's actually the X-rays that absorb on the fuel capsule you see here in the middle. It's kind of BB, sub-BB sized ball. And it's the X-rays that drive the implosion. And it's important to note that this process is roughly about 12% efficient, and it's called indirect drive. So on the NIF, while there's 2 megajoules of energy in the laser, only about 250 kilojoules is actually absorbed, excuse me, on the fuel capsule. And this depicts the general process. That energy is absorbed on the fuel capsule in the plastic ablator, and then the deuterium-tritium hydrogen fuel is inside that. The plastic heats tens of millions of degrees, blows off. and the fuel capsule is imploded, compressed, and is ignited, and a self-sustained burn wave is initiated. And what's very important and significant for the NIF is that the gain of that fuel capsule was 34. So they produced 8.6 megajoules of fusion energy on the record shot, with only 250 kilojoules coupled to the actual fuel capsule. So what we're doing differently than NIF is we have a different illumination geometry, and we're shooting a much larger fuel capsule. So here on the left, you see NIF with 192 beams. We're just going to use 2 beams with much higher energy. And so we'll be able to couple over 8 megajoules to the fuel capsule, whereas NIF is only coupling 250 kilojoules. And the way we can do this is we can beam shape our laser beams to where they're peaked around the intensity, sorry, the intensity around the ring of the laser spot is higher in intensity by about 2-to-1 contrast. So when you do this and you absorb the laser in the target plasma corona, you can get spherical implosion from two-sided illumination. And we published a paper on this target design concept with all 3 major design labs, Livermore, Los Alamos, and the Laboratory for Laser Energetics and General Atomics. And it was an editor's pick in physics of plasma. So I encourage anyone interested to dive in to read the paper. So of course, how do we get to coupling over 8 megajoules to the actual fuel capsule? And we need to lower laser cost. And that's what we're all about at Xcimer Energy. So we're cutting laser cost by replacing glass with gas to enable commercial IFE. And this is an illustration of one beamline where we start with what are called long pulse KrF laser amplifiers operating at about a microsecond. And then steps 2, 3, and 4 are a way we can compress this energy in space and time to the nanoseconds needed for fusion illumination. So steps 2, 3, and 4, these are nonlinear optical processes, and they act like gas mirrors, reflecting the laser light, compressing it in space, compressing it in time, and sending the high energy beams into a target chamber. So here you see our two-sided illumination inside this chamber, which uses a thick liquid wall to protect the steel of the chamber. And coming to that, so this is that chamber with the laser abstracted away. So we will utilizing 2 beam illumination and less than 1 Hz shot rate enables the use of thick liquid wall protection based on the high life design, which was developed in the early days of Livermore in the late 70s and early 80s. So what's great about our approach specifically is with the small number of penetrations and low repetition rate, we can use FLIBE, which is our coolant and tritium breeding material. We can also use it as a first wall protector. So the chamber can last the lifetime of the plant. And we can use currently qualified steels in the construction of the reactor, which is a major advantage. So we'll be shooting one target every few seconds, few gigajoule yield per burst, and collecting the energy in the FLIBE, which then you have to extract the tritium to fill future targets, and then take the heat away from the FLIBE to power a standard steam cycle. So in summary, lower laser cost enables us to build a much higher laser energy than NIF. This enables us to shoot much bigger targets and the robust gain regime of the halide centurion experiments to achieve commercially relevant gain. And the laser architecture enables us to use thick liquid wall protection so that our chamber can last the lifetime of the plant. And this is our roadmap to how we can drive the cost of an nth-of-a-kind plant down to $50 per megawatt hour. So our roadmap, 3 major phases. The first phase, Phoenix, is where we're demonstrating this gas mirror technology that I described earlier, as well as demonstrating that we can build KrF lasers at a microsecond plus pulse length, and we really understand how those lasers operate. The next major phase of our program is Vulcan. This is our break-even machine, where the 4 megajoule laser will achieve wall plug break-even. So that means more fusion energy out of the burst than the laser took off the grid electrically. This system will be upgradable in place directly to 12 megajoules, where we'll be able to serve several national security applications, such as stockpile stewardship and nuclear weapons effects testing in this Vulcan break-even machine. And then finally, by the mid-2030s, we'll build Athena, which is our fusion pilot plant to deliver electrons on the grid. This is showing a depiction of the progression of our Xcimer or KrF laser technology. The first 2 steps are part of the Phoenix program that I just showed on the prior slide. The Argos module is part of Vulcan and Athena. So Argos is what we will mass produce, these laser modules for all future systems. And the LPK stands for long pulse kinetics, and the kilojoule system are our prototype systems that will enable us to develop new pulse power technologies and benchmark all of our laser codes so we can design the Argos module. Here is an illustration of the Phoenix system. Shown in green is complete. Shown in yellow, we have prototypes complete, and then the rest will be completed by Q2 of next year. And here you see a central feature of the Phoenix architecture where we have, and shown in purple, is a long pulse, in this case, in Phoenix, a 250 nanosecond pulse. And then we have that has a lot of energy. And then here, a short pulse that has much, much less energy shown in orange. These beams counterpropagate, and energy is transferred from the beam shown in purple to the beam shown in orange. So as the orange beam crosses that purple beam, it takes energy away from the purple beam. So it effectively reflects laser energy, and it's compressing it in time because the energy is transferred to a shorter beam. LPK, here's a picture of a before and after. So on the upper left is an early design shown virtually in place before we raised our Series A. And then we completed this on time and on budget by the end of last year, and it is now fully operating, and we're actively benchmarking our laser codes and informing the design of the Argos laser module. So switching gears a little bit to thinking about what is needed for fusion on the grid by 2035. So first, fusion performance. I think most approaches require a break-even demonstrator along the way. You have Spark for CFS, you have Vulcan for us. Other approaches have similar concepts. So it is really important for a given approach to demonstrate wall plug or facility or engineering break-even. All those terms are very synonymous. Finally, experience. Fusion startups need to learn by doing. And this is important because the past major big machines like the Z machine, the Jet Tokamak, NIF, one, these were all built decades ago. So the designers and builders have retired, and these were one-offs. So industries were not, supply chains were not industrialized to support mass manufacture of the components for these one-off machines. So companies have to learn by doing. Companies have to not just learn how to build complex machines, but learn how to build teams that can build the complex machines. And this takes a lot of iteration. And this is sometimes often overlooked in thinking about timelines. Also, talent. You need the best people in the world. And as I mentioned, there's a lot of great scientists who worked on the development of the machines in the government decades ago that are now in their 70s and even older. And so companies need to consult with these individuals and help them educate younger generation of workers at the companies for knowledge transfer, especially for Xcimer. A lot of our technology was originally developed in the 1980s during the Cold War. So we have several people who worked on laser missile defense projects where that was well funded back then and not now, of course, helping train and educate younger generation of workforce at Xcimer. And then finally, money. Of order, it's a few $1 billion per mature scientific approach to get to electrons on the grid. And that's a lot of money. And typical VC models are very gated. You tackle the high risk things first before deploying a lot of capital to move forward. And in fusion, to get there by the mid 2030s, a lot of parallel development has to go at the same time. Not just the major de-risking like fusion performance or engineering break even, but supply chains and other lower risk technologies such as flied pumps, et cetera, but technologies that need significant capital to develop. So government investment can encourage more risk taking from investors and enable more parallel path development, which will be needed to reach our goals of mid 2030s deploying electrons on the grid. Finally, the long lead items for commercial fusion. Of course, tritium technology, all companies will require large-scale tritium handling, at least a few hundred grams of tritium or more, and no fusion pilot plant has built to date with tritium systems in place. So that technology needs to be scaled and is shared among all companies burning DT, which our position is all the first power plants are going to be DT based. Of course, raw materials, the big ones are lithium, beryllium. These are blanket materials. Depending on approach, whether it's FLIBE or lithium lead, there are a lot of mass of raw materials are needed to build the blankets for these machines. Solid state switches used by all pulse power approaches, including Xcimer Energy, because our lasers are pulse power devices. And this technology development is a 5 to 10 year time frame. And finally, construction, siting, permitting. States need to get educated on how to license not just reactors, but break-even machines. And this takes time and design cycles. Finally, wanted to comment, fusion is a global race, and China is moving fast. China is currently building a larger version of NIF in Myongyang. There's a lot of debate as to what energy level this will be at, but seems like it will definitely be over 3 megajoules, and they have the billions to spend to build a solid state system at several megajoules of energy. And Xcimer, on the laser side, our company is the only path for the US to compete on both speed and laser energy in order to compete with China. Because if China builds this, they're going to have a stockpile stewardship capability that surpasses the United States. So it's not just energy security, but also other national security items that the US needs to be concerned about with respect to China. And then finally, to conclude, we need more money in the Milestone Fusion program. There's $50 million were allocated to 8 companies. And in the NASA COTS program, it was roughly $500 million that went to 2 companies. So we really need to step up our game in the United States, educate members of Congress, and educate the public the importance of public-private partnerships and bring more money into the program. And with that, I'll conclude and thank you everyone for listening to me talk a little bit about Xcimer and our views on the fusion industry. Thank you.